Good afternoon. Today I'm going to do a calculus problem, disk method. I'm going to find the volume of a 3D object using the disk method of calculus. In particular, we're not going to use the screen much. I'm going to go to the board here in a second, but we're going to find the volume of the solid generated. Find the volume of the solid generated by revolving the shaded region about the x-axis. And this shaded region that we're talking about is this region here. It's bounded by the y-axis, aka x equals 0. It's bounded by the vertical axis, x equals pi over 4. And I promise I'll go to the board. And the graph y equals 6 times the secant of x, which is this little curved piece here. And the region is the gray region, and we're going to take this region, we're going to revolve it about the x-axis, which I'm fixing to change its name to the theta axis. We're going to take this region, revolve it around the x-axis like this, out toward our faces, and into the computer screen. We're going to get a 3D object, and we want the volume of that 3D object. Okay, let's go to the board. I redrew it just so we could see it better. Now I'm going to do some relabeling. I'm calling the x-axis the theta axis now. I'll try not to refer to it as x anymore. I'll try to catch myself if I do. Here's the y-axis. Now the z-axis, I'm defining it to be the axis that comes out toward our faces in 3D out of the board, and it comes into the board as well. It goes into the board and out of the board. That's the z-axis. The y and theta are as before. I replaced x with theta. And that's not a very good looking theta that I drew there, but that's theta. So theta yz, and again the region is bounded by theta equals 0, theta equals pi over 4, and y equals 6 times the secant of theta. I'm using theta instead of x. So again, there's the theta axis, which was my old x-axis. Here's y. So I'm going to revolve this about the theta axis. What used to be my x-axis, and now it's my theta axis. And I'll get this blowhorn looking object right here. That's my 3D object. I tried to draw it. I can't draw too well. Now, here's the deal. Notice that inside my region, my striped region, which is my region, I've got a little thin black rectangle, infinitesimally thin, with thickness d theta, a very small thickness. And the height is 6 sec theta. Or should I say approximately 6 sec theta. Okay, so that's called my cross-sectional rectangle. And if we were to make these rectangles infinitely thin and add infinitely many of them within the region, and let's just say that they are all the same width. They don't really have to be the same width, but let's just say they are. We would get the perfect area, would get the area of this striped region. That's from Calculus 1. We know that from our integration, just in the 2D plane. But we want to go a little further this time. We want to go 3D. We're revolving this whole region about the theta axis, which was my old x-axis. We're coming out of the board. We're going to come in. We're going to do a sort of a YZ. We're revolving about theta, and we're coming out of the board. So this rectangle right here is going to, when we revolve this region, this rectangle is going to come with it. And it's going to form a disc in the YZ plane. I didn't really do a good job of drawing it, but let me use my fingers. It's a disc and whose cross-sectional circular areas are in the YZ plane. Follow my finger right here. We're in the YZ plane. Now the thickness is along the theta axis, or the old x-axis. It's a very, very small thickness. It's infinitesimally thin along the theta axis. And the circular cross sections go along the YZ plane. Okay, now what we're going to do is, since those discs, they're not cylinders, they're discs. I should have said discs earlier. If I said cylinders, forgive me. They're discs, and what we're going to do is we're going to add the infinitely many of the infinitesimal volumes of those infinitesimal disks. This horn right here is the volume that we're after. And this horn can be chopped up into infinitely thin disks whose infinitesimal thickness lies along the theta axis. And if we can, that's a little informal. To say that I'm adding infinitely thin things is a little informal, but for our purposes, that'll do. We won't get into analysis here. So I want to add infinitely many volumes of these infinitely thin disks whose cross-sectional areas lie along the YZ plane. And that'll give me this volume. In other words, I'm going to do the integral. To add infinitely many of these infinitely thin things, I need an integral. Now, for the cross-sectional YZ areas, I do a sub theta. Theta is my old x. A sub theta is pi, quote-unquote, pi r squared. Now, the radius is, I'm finding the area of a cross-sectional circle along our infinitely thin disk. I'm just finding a cross-sectional circle along the YZ plane. And this radial chord is along the YZ plane. And again, that's going to be 6 sec theta. And that's true because that stems from this. When we revolved, if I said rotate earlier, forgive me, we revolved. So that comes from this right here. Let me back up. This right here, 6 sec theta, comes from this 6 sec theta right here. Because we revolved the rectangle as well. It came with the whole region. But there's actually infinitely many more where that came from. Okay, so there's 6 sec theta. That's the radius, here's my finger, along the YZ plane. So that would be a radius like this. Wait, no. It would be a radius, excuse me, it would be a radius like this, along the YZ plane. We're not moving along the theta axis at all. So a YZ radius from center to the edge. And then now the thickness, that is the theta axis, the old x-axis. But we're not going to use that for the area though. We're just going to use the radius. So pi r squared, that's pi times 6 sec theta quantity squared, because my radial chord was of length 6 sec theta. Pi r squared is area of the circular cross section along the YZ plane. And then, so pi 6 sec theta squared, that's 36 pi secant squared theta. And we just do the square there. We get that. So that was area of theta. That's the circular cross-sectional area. Now, if we take that circular cross-sectional area and we multiply it by the thickness along the theta axis, d theta, we get the infinitesimal volume of that infinitesimal disk. We're adding the volumes of infinitely many infinitesimal disks. So there's that. Now, since we want to add all these together, we're going to stick an integral here, and we're going to stick an integral here. That's pretty much what this amounts to. That's what we're going to do. And we're going to integrate from theta equals 0 to pi quarter. And when we do the disk method and washer method, we integrate along the axis that we revolve around. If I said rotate earlier, forgive me, I meant revolve. So we integrate about the axis we revolve around. Now, we're using discs and not washers because discs don't have holes in the middle and washers do. And that was my poor attempt to draw a disc. So the volume is the a to b integral a sub theta d theta, which is the 0 to pi over 4 integral of just the area is pi r squared, which is the r, quote unquote, is 6 sec theta. And then, so I got that. Now I square. I got 36 sec squared theta d theta. And now the 36 comes out, and I just got the 0 to pi quarter integral, sec squared theta d theta. But we know what that is. That's the antiderivative tan theta when we do the integral. And then we integrate from 0 to pi over pi quarters. And then that's just 36 times the tan of the upper limit minus the tan of the lower limit. But tan of pi quarter is 1, tan of 0 is 0. So there's that, and that's 36 pi. So 36 pi is the volume of my 3D object here. That's the final answer. So that was my total volume. Thank you guys, and I hope that helped.